Good morning, everyone. Thanks for joining my webinar today on polyglot persistence with Neo4j and MongoDB. So as Corey said, my name's Will. I work on the developer relations team at Neo4j. Be happy to chat with anyone after the webinar. So my contact details are up on the screen there. Feel free to reach out. So, like I said, I work on the developer relations team at Neo, and that means I talk with a lot of users who are either getting started with Neo4j or they're integrating Neo4j into their existing architecture. And a question that comes up a lot is, does Neo4j work with fill in the blank here? And these can be things like the languages that I'm using. Can I use Neo4j from JavaScript, Python, Golang, all of these things. And for this, the answer is usually yes. We have drivers in lots and lots of different languages. So this is usually a question that comes up. Also, does Neo4j work with my framework? I'm using Spring. I'm using Ruby on Rails. Does Neo4j work with that? And the answer is, of course, yes. We have great integration with Spring through Spring Data Neo4j. We also have a Ruby driver that integrates with Rails. What about processing frameworks like Spark? And again, yes, we have integrations with Spark so that you can run graph processing jobs in Spark, pulling data from Neo4j and write those results back. What about Docker? Can I use Docker to deploy Neo4j? What about other databases? Can I use Neo4j in a polyglot persistence environment? This is what we're going to be talking about today. And these are really, really important questions, and I think it's really good when you're introducing a new technology into your stack to understand, what the answer to these questions are for the tools that you're using and the tools that make sense for your application. So today we're going to be talking about one of these questions in specifics. Does Neo4j work with MongoDB? So before we get into this, I think it's really important to understand why we would want to use Neo4j and Mongo together. So let's look at Mongo. Mongo is a type of NoSQL database. The data model is a document. So you can think of JSON. We're storing JSON documents. We have very complex queries that we can run on these with full text search. Mongo is really good with scaling out, so it shards the data across many, many machines. There's no schema, so we have a flexible document data model here. And the use cases that make sense for Mongo are things like a product catalog, user profiles, storing content, things like this. And today we're going to focus on the product catalog use case, so we'll come back to this. So that's Mongo. So what is Neo4j? And so for those of you not familiar with Neo4j, I'm going to spend just a few minutes talking about graphs and Neo4j at a high level, and then we'll dive into some more advanced technical content. So if you're familiar with Neo4j, just bear with me for a minute here. So Neo4j is a graph database, and when we're talking about graphs, we're talking about the data structure of nodes and relationships, so connected data. Graph databases have a property called native graph processing or index-free adjacency. That means that we can traverse the graph very, very efficiently without looking up an index. This has implications for the use cases that make sense for a graph database. And of course, we need some way to query the data as a graph, and that's where Cypher, the query language for graphs, comes in, which we'll see more examples of in a minute. So let's talk about the graph data model a little bit. So we call this the property graph model or the labeled property graph model. So nodes, these are the entities or the objects in the graph. We have optional labels that we can store on these nodes. So here we have 2 nodes with the label person, 1 node with the label car. We can also have key value pair properties that we store in the node. So here we have the key value pair name Dan, the date Dan was born, his Twitter handle, and then for our car node, we have the brand of the car, the model, etc. Relationships, these are the connections between the nodes. Similarly to a node's label, these have types. So we can say here that Dan loves Anne, Anne owns the Volvo. Note that relationships have a direction, and we can also store key value pairs on the relationship. So here we're storing the date since Dan has been driving the car as a property on the relationship. So this is the basic data model that we work with graph databases and Neo4j. So I mentioned Cypher, which is the query language for graphs. Cypher is all about pattern matching. We use parentheses to indicate nodes, and then properties within curly braces on the node. So the pattern we're defining here is 2 person nodes, 1 with the name Dan, 1 with the name Anne. In brackets, we have a loves relationship. We use brackets to define relationships, and this is a create statement. So if we ran this against Neo4j, this would create 2 nodes in our graph, 1 for Dan, 1 for Anne, with a loves relationship between them. So this is the basic point of Cypher, all about pattern matching. And we'll see lots of Cypher in a minute here. I want to talk about some use cases that make sense with graphs and in Neo4j. The first one is real-time recommendations. We're going to come back to this in the context of our product catalog use case, but I want to talk about this just a little bit. So we've all seen recommender systems on Amazon or Netflix. Here are movies you might be interested in based on movies that you've watched, things like this. So the data model for recommendations might look like this, with users and the products that they've viewed or the products that they've purchased, and then we can generate recommendations for them by traversing the graph. Another really common use case for graphs is master data management. So any large enterprise has many, many different systems for storing information about their customers, their employees, their business partners, their processes, inventory. All of this might be stored in many, many different systems throughout the organization. And the graph data model is flexible enough to allow you to store either metadata about that information or bring in that information from disparate sources so that you can have, for example, an entire 360 view of a customer in the graph. Fraud detection is another common use case for graphs, especially within the financial services industry. A typical example here is of a fraud ring where you have many individuals working together, sharing pieces of an identity to submit fraudulent credit applications. So they may share a social security number, an address, a phone number across the group. It's very difficult to find these rings using a standard relational data model. But when you model that as a graph, it's much easier to uncover fraud rings. Graph-based search is another use case for graphs in Neo4j. Think of LinkedIn. When you search for someone, type in Michael, you don't see all of the results for Michael in alphabetical order across all of LinkedIn. No, you see the results sorted by their connection to you. So you start to see your first and second and third degree connections first, as you're typing in there. So graph-based search really helps with finding relevant information while a user is searching your application in the context of that user. Network and IT operations, think of a data center or a more complex application deployment. Think of all the dependencies in there. If you model that as a graph, you can run queries that will tell you if this database server goes down, what are all of the applications that are impacted by that. So network and IT operations is a natural graph problem as well. And the final use case I want to talk about with graphs is identity and access management. So in an organization, think about all of the different documents, folders, files, and permissions across the organization. This is, again, is a natural graph problem because we may have rights that come from belonging to a certain organization, a certain role that we have. This can be represented as a graph as well. So really, at Neo4j, we have this saying that graphs are everywhere, and really once you start thinking in terms of graphs, you really see graph problems, problems that can be solved with the graph data model everywhere that you look. Okay, so that's a brief overview of Mongo and Neo4j. But back to this question of why would we use these two together? So now that we understand what Mongo is and what Neo4j is, some use cases that make sense for each of them, why would we use them together? Well, I think it's helpful to take a look at the traditional approach towards data. So from the relational database world. So traditionally, data looked like this. We had systems of record that were storing information about very discrete data points. We would mash these into a data structure, table, and rows, store those in a relational database, and we would use that same relational data model across every function in our organization, from HR to logistics to customer support and so on. But something is changing, has been changing for a while. Really, we've been shifting towards what we'll call systems of engagement. So rather than storing discrete pieces of data, instead we have users that are engaging with devices. We have users engaging with other users. So think of social networking, all of that. And with Internet of Things, we have devices engaging with other devices. And all of these interactions are generating lots and lots of data. So sort of the biggest result of the shift towards systems of engagement are this huge growth in data volume. And I think it's important to point out that we're really only here in the curve and that we have really a long way to go before we see many, many more exponential increases in data volume. So this really presents an opportunity for organizations to take advantage of this data. So comparing the standard relational data model, systems of record, with systems of engagement, this is what brought us the NoSQL world. So instead of very structured data models defined by a schema, instead with the NoSQL world, we have more flexible data models. Instead of pre-computed, we need real-time queries. We need to do real-time recommendations. It's not helpful if we have something pre-computed that we're serving up to someone who wants to watch a movie. We need to make sure that's a real-time query. And the data is very contextual. We need to represent this in the context of the user. So the NoSQL world brought us things like document databases like Mongo, column stores like HBase and Cassandra, key value stores like Redis, and graph databases like Neo4j. And so these all have very different data models. Some of them have different use cases that make sense. And so instead of using the relational data model across all functions of our organization, we start to see things like this, where we may be using cache for storing user sessions. who may be still using a relational database for financial data, who may be using a graph database for recommendations, who may be using Mongo as a product catalog. And this is what polyglot persistence is all about, is using different types of data in different ways, recognizing that different database technologies have their strengths and that we should use them for different functions in our organization. We can use them together to enhance our application or our enterprise data. So in the polyglot world, the architecture for a typical e-commerce application might look something like this, where we're using Redis, a key value store for our shopping cart because we have an ID for the session. We don't really care what we're storing in there. We just need to make sure that's very, very scalable, that we can do writes and reads very, very quickly. Maybe using Mongo for a product catalog. We'll talk about the specific advantages there in a minute. And then we may be using Neo4j to generate product recommendations and maybe store some of the social graph if that's important for our application. And it's not just our application that's integrating and talking to our databases. We have data scientists, we have internal BI teams that are querying our database directly for reporting and ad hoc analysis, things like this. So really, the benefits of polyglot persistence don't come for free. Instead, we have some added complexity here. So I want to talk about some of the challenges of polyglot persistence, and then I want to talk about some of the tools that we have at Neo4j, specifically some of the tools that my team has worked on that make polyglot persistence with Neo4j a bit easier. So the first challenge that I want to talk about is data sync. So if we're using multiple databases for our application, how do we keep the data up to date? If we're introducing Neo4j into an already existing infrastructure, let's say we're using Mongo or a relational database, we have a few options for migrating the data. We could migrate all of the data to Neo4j, and then all of our queries go to Neo4j from the application. That might not make sense for some of our use cases. So instead, we might want to migrate just a subset of the data. So the graphy data goes to J, the non-graph data goes to our relational database or to Mongo, and then our application knows that, okay, for graph queries, we go to Neo4j, for non-graph queries, we go to our relational database or our document database. And then we have a third option where we're going to duplicate a subset of the data. So we're still using our document database for initially storing all of the data, but then we're duplicating the graphy data to Neo4j so that graph queries now go to Neo4j, non-graph queries go to our document database or whatever else it is. But we need to keep that data in sync across our two databases somehow. So let's take a step back and look at a use case where it might make sense to use Mongo and Neo4j together. So consider a course catalog. So this could be for, let's say, some online MOOC system where we have courses that we can take online. We need to be able to search by keyword, filter by category, filter on a date range, and then there's lots and lots of detailed text that needs to come back in one database query, ideally, to populate this view in our application. So return potentially lots of HTML to populate the view, images, things like this. And this is a great use case for Mongo. So earlier we saw that product catalogs are a core use case for Mongo. And that's because Mongo has good JSON storage of all of the text and images that we need to store. We have support for full text, things like this. So if we were going to store a course catalog in Mongo, the data model might look something like this. So here we have a collection in Mongo. Instead of tables, you have collections of documents. So here we have a collection called course, and this is a query that returns a single document representing one course in our catalog. So this is a course called Designing Technology for Learning, and we can see we have an array of categories for this course, so information tech and design, engineering. We have information about the university that's offering this course, and you can see we're storing HTML for the course syllabus and the description and URL for the photo. So we would be returning this document along with many others to populate that view in our application. And by the way, the code for generating this sample data that we're going to walk through is online. It's just a simple Python script that goes out to the Coursera API and grabs all of the English language courses from Coursera, stores those to Mongo, and then it also generates some fake student data, which we'll look at in a minute. Yeah, so all that data is online. I'm sorry, the Python script to generate all that data is online. Great, so back to our application here. Okay, so we're going to use Mongo to power the course catalog piece of this. That's great, but something's missing here. So I like to say, well, what about Bob? So all of this is done in the context of the user, in the context of Bob. And our application knows what courses Bob has taken and knows how Bob has interacted with our site. So really, we should be serving personalized recommendations to Bob. We should be saying, based on courses you've taken, here are some courses that you might be interested in. So these are personalized real-time recommendations that can help drive engagement with our application. So we saw earlier that the core use case for graphs and Neo4j are real-time recommendations. So I want to talk a little bit about the data model for that, how that works, and then we'll look at some data from our course catalog application. So the most simple graph-based recommendation, the data model would look like this. So here's a node for Will. I took some class. This class was data structures. We also have Amelia, who took data structures. And then Amelia also took this class, Advanced NoSQL. So if we're going to do a graph-based recommendation for me, for Will, what we would want to do is look at classes that I've taken, who else has taken those classes, and then what other classes have those other students taken that I haven't taken yet, because those are courses that I might be interested in. So in this case, we would recommend Advanced NoSQL to me because I took data structures, Amelia took data structures, and Amelia took Advanced NoSQL. So we have some measure of similarity between Amelia and I, and similar users are likely to be interested in similar things. So this is the most simple collaborative filtering data model for graph-based recommendations. And we can represent that in Cypher like this. So here we're using a match clause with match as similar to a select statement in SQL. So here we're matching on some person node that's named Will. We're traversing out from Will along this took class relationship to find classes that I've taken. Then we're traversing out again to find people that have taken the same classes of me. Then on line 2, we're traversing out from those people to find courses that they've taken where I do not have a relationship to those courses, and we're returning those as recommended courses for me to take, ordered by the number of paths that we've seen, so the number of students and overlapping courses connecting them to me. So we can see here, well, great. So for our Polyglot course catalog application now, we can use Mongo to power our search and filtering, and we can use Neo4j to power our personalized recommendations. The only problem here is how do we keep the data in sync? So we know we need to be querying courses and student information in Neo4j, but we're using Mongo, so how do we get the data into Neo4j? So we have a few options to do that. The first one that I'm going to talk about is using APOC procedures. So APOC stands for Awesome Procedures on Cypher. This is a library of procedures for Neo4j. This is available on GitHub. It does not ship with Neo4j, but anyone can download and install these. So if you're not familiar with procedures in Neo4j, with Neo4j 3.0, we introduced the concept of user-defined procedures. So this is code that's written in Java, deployed to the database, and then can be called from Cypher. So you can think of it as a way of extending the Cypher query language. And Neo4j ships with some built-in procedures. So there are procedures for listing all of the labels or indexes in the database, in the data model. So we can call db.labels. That will return one row for every label that we have in the database. But we also have custom user-defined procedures. So anyone can write these. There's a template on GitHub if you want some structure for how to write your own procedure and deploy those. But you don't have to write your own procedure to take advantage of the power of procedures. This is where APOC, or the Awesome Procedures, come in. This is a library of, I think we're close to almost 200 procedures now that are in this library. It's a single jar file that you just have to download and drop into Neo4j. And there are a ton of things in here. So if there's a time that you're wondering, I wonder how can I do that in Cypher? How can I do that from Neo4j? Chances are that there's a procedure for that in APOC. So things like loading data from relational databases. So there's a procedure that can use the JDBC driver to load data into Neo4j directly from relational databases. There are procedures to load data from the web in JSON, XML. So how does this help us with getting data into Neo4j from Mongo? Well, one of the many interfaces for Mongo is their REST API. So Mongo exposes a very simple REST API that we can call that will return JSON. So we can specify some simple queries here, like the name of a collection, the name of the database, limits. We can do some simple keyword searches, things like that. And we saw that we had a load JSON procedure in APOC. So we can use that with the REST API for Mongo to bring data into Neo4j. So what does that look like? So if we curl the endpoint here for course catalog course, we get back some JSON that has all of the documents from our course collection. So let me just switch over. So here's Mongo, course find one. So this is just going to return a random document. So I'm running Mongo locally here. Here's this looks like the same Georgia Tech designing for learning course that we had. So I'm running Mongo locally here with this course data already. So let's see how we can use APOC to pull this data into Neo4j. So here I'm running Neo4j locally. Let's make sure I don't have any data in here already, so we'll just match on everything, return the count, and we have 0. So I've installed APOC. The first thing I'm going to do here is just query MongoDB using load JSON. So the syntax for this looks like this: call apoc.load.json, and then we specify some URL. In this case, we've exposed Mongo on localhost port 28017. We want the course catalog database, and we want all entries in the course collection. We then want to iterate over the rows array in this JSON document, and then I'm just going to return the first 10 entries. And you can see what we end up with are 10 rows, so 10 maps or dictionaries here. So we get back the data in Neo4j as a map or a dictionary. So here you can see how that same course is represented as a map. So that's good. Here we haven't written anything to Neo4j yet. So let's load all of our courses from Mongo into Neo4j. So what does that query look like? So again, the first bit is the same here. We're getting all of the courses from the course catalog database. We're iterating over this rows array. Then each course has a project ID that uniquely identifies the course. So we're using the merge statement in Cypher. This is like a get or create, so we won't duplicate any course nodes here. Then we set the course. Then we iterate over all of the categories. So we saw we had a category array. We create category nodes and then connect the course to the category. And then we do the same for the university array. So a course can be offered by one or more universities. So we create a university node and we create this offered by relationship. So we say that a course is offered by the university. And if we run this, it pulls in all of our courses from Mongo and creates those in Neo4j. So now we can query the graph. So here, this query is going to find courses where the course name contains the string matrix, and we get back coding the matrix, which this is one of my favorite Coursera classes. This is a linear algebra course, but all of the coursework is done programming in Python with matrices. So really, really cool course. Anyway, so we get back this course node. We can expand from the course and we can see the category that this course has represented here as a graph. We can see that it's offered by Brown University. We can traverse out from Brown University and see the other courses on Coursera that are offered by Brown. Here's one exploring neural data that shares a category with coding the matrix. It shares statistics and data analysis. Cool, so what have we done here? Well, we've pulled data in from Mongo just using Cypher, and we're able to query that immediately in Neo4j. So we haven't left Cypher to do our data import, which I think is really, really cool. So we wanted to do recommendations. That's our use case here for our course catalog. So let's take a look at how we would find courses similar to coding the matrix, because I said this is my favorite course on Coursera. So a very safe recommendation would be to find similar courses to coding the matrix to recommend to me. So How could we do that? Well, let's take a look at this query. So here we're matching on courses that contain matrix, and we know that we're only going to get back coding the matrix. That's the course we want to start with. So now we start with that course, and then we traverse out to the category nodes, and then from those category nodes, follow the incoming has category relationship to find other courses. So here we're going to find other courses that have the same categories as coding the matrix. Then we're using the size function here on a pattern. So we're saying size of coding the matrix offered by a university, and then following the incoming offered by relationship to our recommended course. So here we've aliased our recommended course to this rec. So what does this mean? Well, this is saying, okay, if our recommended course is offered by the same university as coding the matrix, so in this case Brown, then the size is going to be, so the result of this function is going to be 1. Otherwise, if this pattern doesn't exist, it will evaluate to 0. We're going to alias that value to same university. So same university will be 0 if my recommended course is not offered by the same university as coding the matrix. Otherwise, it will be 1. And we're going to use this when we compute a weight for the recommendation on the next line. But we're piping through the recommendation and then count of the number of paths as common categories. And then we're returning the recommended course, the number of common categories, whether or not it was the same university. And then we're computing a weight score here. So we're taking the number of common categories, so the number of categories that this recommended course shares with coding the matrix, and we're adding same university times 2 and calling that the weight. So with recommendations, it's often the case that we have many different scores that we want to factor in to some weight that we're then ordering the recommendations by, because we want to return these, we want to show the most relevant recommendations to users first. So we need some average weight for this. So in this case, we're combining the number of average categories with, and then boosting that recommendation score if this is offered by the same university as coding the matrix. We return these and order by the weight. And we get this table here with some results. So our most relevant recommendations here is a course named Enhance Your Career and Employability Skills. It has 4 overlapping topics, and it's not offered by Brown, so it has a weight of 4. And we can see the other recommendations here. I want to point out, here's this Exploring Neural Data course. It only has 1 overlapping category with coding the matrix, but it's offered by the same university, Brown, so it has a boosted score, so it appears higher. There's a better chance that I'm going to be interested in this course because it's offered by a university from a course that I thought was awesome. So there's a great chance that this course is going to be awesome too. Okay, so that's a simple Cypher query that we can use to find courses similar to ones that I like. Let's jump back to our slides here. So these are the queries that we ran through. Just leaving these in the slides for reference, so you can refer to those later. Okay, so Milton has a great point here about live streaming. So if we're talking about our course catalog application, we need to make sure that as users are registering and taking courses, that we're keeping that data updated in Neo4j. So we need to be streaming data to Neo4j. we can use APOC. We can sort of put that on a cron job to batch update, but really we need some trigger, some way to stream updates from Mongo to Neo4j to make sure that we're not serving stale recommendations, because there's nothing worse with a recommendation than recommending a movie that the person has already seen or a pair of shoes that they've already purchased. That's just a useless recommendation. So we want to make sure that we always have the most up-to-date information when we're generating a recommendation. So the second option that we can look at for getting data from Mongo to Neo4j is the Neo4j Doc Manager. So Neo4j Doc Manager, this is a Python command line tool that syncs document updates from Mongo into Neo4j, and it handles the conversion from document to graph model automatically. So we saw when we were using Cypher and APOC that we had to explicitly define our data model, the nodes, the labels for the nodes, properties, all of this. We had to explicitly define that in Cypher. With the Doc Manager, that transformation happens automatically, and we'll see in a minute what that looks like. So how does Doc Manager work? Well, Mongo has a data structure called the oplog that's used for replicating data within a replica set. So within a bunch of Mongo instances, replicating data back and forth between them. You can think of this as a transaction log. And so the Doc Manager tails or subscribes to updates from the oplog and listens for writes. And anytime there's a update in Mongo that is converted to Cypher, converted to a property graph model write, and is immediately streamed into Neo4j. So you can think of this as documents into Mongo results in graphs in Neo4j. So how do we convert a document to a property graph? So what does that look like? Here's a JSON document. This is a talk from a conference. We have a couple of sub-documents here, session and speaker, with some various properties. If we were to insert this into Mongo and using the Neo4j Doc Manager, this would be converted into a property graph model that looks like this. So talk is the name of the collection. So the root document becomes a node with the label talk from the name of the collection. We store the object ID and the root level properties from the document as properties on the talk node. Then the sub-documents, so the documents with the key session and with the key speaker, these become nodes themselves. The labels come from the keys of the sub-documents, so session and speaker become labels on these nodes. And then we store the properties of the sub-documents on the nodes themselves with a relationship to the root level document. And the relationship type for that connection to the root level document has the collection name, so talk, and the key for the subdocument. So the relationship type connecting talk and speaker becomes talk speaker. So this is how we convert documents to graphs. You can think of a document as being able to be naturally represented by a graph using this mapping. So I said that Neo4j Doc Manager is a Python command line tool. So it's on PyPy. You can install it with pip. Just pip install Neo4j Doc Manager, and then you use that second line Mongo connector, specify connection string for Mongo, specify the connection string for Neo4j, run that, and updates to Mongo will be immediately synced to Neo4j, which I think is pretty cool. So let's look at a demo using Neo4j Doc Manager. Before we do, because we're going to look at some methods for generating course recommendations, we talked about this a little bit, but I want to point out that there are two general approaches for recommendations. The first is content-based filtering, so recommend items based on what users have liked in the past. So this is what we did with Coding the Matrix. We found courses similar to Coding the Matrix and recommended those to me. The other piece is collaborative filtering, and this is what we saw at the very beginning when we were talking about a course that Will had taken and a course that Amelia had taken, right? So this is finding similar users in the data set and making the assumption that similar users are going to be interested in similar things. And really, in production, most recommendation systems are using some hybrid approach of both of these, but these are sort of the extremes. Okay, so let's jump back into Neo4j. Let's clear out everything. Okay, so we've deleted everything from Neo4j, so nothing in there now. Let's go back to Mongo. And okay, so we've cleared out Neo4j, we've deleted our course catalog database in Mongo. I have installed the Neo4j Doc Manager locally here. So let's go ahead and run that. So now Neo4j Doc Manager is running. It's now listening for updates in Mongo, and any updates that it gets in Mongo, it's going to convert those automatically to a graph in Neo4j and write those to Neo4j. But we need some data. So I mentioned this Python script. So this is what's out on GitHub. This goes out to the Coursera API, English language courses, and then uses this awesome Python library called Faker to generate some fake data about student profile information, writes those to Mongo, and then chooses some courses at random to assign those to students. So we inserted 400 courses from 91 universities, almost 500 instructors. We generated 500 students at random. Wrote all of that to Mongo. So let's jump over to Mongo. So now we have this course catalog database. And let's find a course. Okay, and here we go. Here we see our very familiar course from Georgia Tech on designing for learning of technology. Great. So all our Python script did was write this to Mongo, and we had the Mongo connector Neo4j Doc Manager running here. So all of our updates were converted to a property graph and written to Neo4j. So I'm just going to grab the object ID of this course here, and let's see if we can find this course in Neo4j. So this cipher statement, this just says match on some course node that has this ID, and then traverse out one relationship, and then find this course taken node and students connected to this. So what is this doing? It's just going to find this Georgia Tech course, traverse out one relationship to find things like the category, traverse out on this course taken relationship. So this represents a session. So here, Casey O'Keefe took this Designing for Learning course, and we're storing the date and the grade and things like that. And again, this is all just random data. Cool, so it looks like this worked. So we've automatically synced data from Mongo to Neo4j. We didn't have to do any data model conversion. That was all handled for us. And any further updates are automatically streamed to Neo4j. So that's really cool. Let's see now how we can generate some recommendations for Casey O'Keefe. So we saw before when we were traversing out from coding the matrix to finding similar courses, we did that by category, but we were just starting at one course. Here we want to start with the student and look at the courses that Casey O'Keefe has taken, and then we want to find what are the categories of those courses, and we're just going to aggregate on the number of categories in each one. And here, looks like Casey O'Keefe has not taken very many courses and confined us within engineering and information tech and design. So this might not be very interesting, but we'll go ahead and try it anyway here. So the first thing we can do is generate recommendations based on content. So here we're just going to use the category of the course. And again, this is very similar to what we did previously. Here this is just shorthand for starting from Casey O'Keefe, find all of the courses that this person has taken, what are the categories of those courses, then find other courses with the same category that Casey has not taken, and recommend those with a count of the number of overlapping categories, the paths through those. So we're recommending engineering life, MRI fundamentals, introduction to systems engineering, computer networks. So these are courses that Casey might be interested in based on the content. We can also do some simple collaborative filtering. So here we're starting with Casey, finding the courses that Casey has taken, finding other students that have taken those same courses, what are other courses that these students have taken that Casey has not taken. We'll return those as recommendations, ordering by the number of paths that we found leading to that course. And we get how viruses cause disease, fundamentals of fluid-solid interactions, and so on. And because this data is random, we just sort of chose courses for students at random. This might not be particularly relevant, but that is the approach that we would take. Cool. And again, all of the slides, all the queries are in the slides here, so you can see how that works. Great. So the last challenge with polyglot persistence that I want to talk about is operations. So with our course catalog, we're using Mongo, and we're getting all of the power of the document database. We're using Neo4j to generate recommendations, and that's great. But now we have multiple databases that we need to maintain and to deploy. Docker is a tool that makes deployment much simpler, and at Neo4j we love Docker. We have an official Docker image, so you can simply say Docker pull Neo4j. Docker will pull down the official Neo4j image. You can run that locally within a container, so you don't have to deal with installation, Java dependencies, all of this. That's great. What I think is really powerful are tools like Docker Compose. Docker Compose allows you to define configuration for multiple containers in one configuration file, and then spin up your application using just a single command that will then pull down all of the images and build those containers that you specified. So for our example, if we wanted to run Mongo and Neo4j and the Neo4j doc manager, so basically the architecture for our course catalog that we talked about, a Docker Compose configuration file would look like this. So we'd specify one container running Mongo, one container running Neo4j, one container running the Neo4j doc manager, and we can link those so the doc manager and Mongo connector container needs to be connected to the Mongo container and the Neo4j container, and then we can specify even the command at startup to install doc manager and to run that. And then with this configuration, all we have to do is say Docker Compose up, and we can very easily pull down the images and start our application. And then we can deploy that. We can run this locally. We can deploy this on AWS or wherever. So Docker Compose makes working with polyglot architecture much nicer. Finally, I just want to mention a few resources that are available out there. Couchbase is a document database, so has a similar data model to Mongo. One of our partners built an open source Couchbase and Neo4j integration similar to the doc manager. So if you're using Couchbase instead of Mongo, certainly take a look at that as well. The developer page, so neo4j.com/developer, is the home for a lot of this more technical content about our integrations. We have sample code for different use cases with Neo4j, so this is a great resource. Definitely check this out. And finally, the links for our integrations and then the documentation for the project that I talked about today. So thank you.